Okay, then section 5.2. This is linear combinations of normal random variables. And this actually goes back to what we learned in section 2.6, so it is actually useful. We do use it later on. Let's say that x has a normal distribution with mu and sigma squared, and a and b are just constants. What is the expected value and variance of a new random variable y, which is ax plus b? So let's look at our expected value of y. This is kind of a review of section 2.6. This is the expected value, well, y is really ax plus b. And do you remember what the rules are for expected value? What happens to those a's and b's? They just kind of come right out, so it's going to be a times the expected value of x plus b. Or the expected value of x, that's the mean, that's just mu, because they told you that was your expected value. So, a times mu plus b. Here, let's write a note up here. Expected value of x was mu, and the variance of x was sigma squared. So that's the expected value for y. For your variance, let's remind ourselves of variance rules. Variance of ax plus b is going, let's see, what happens to the a? The a can come out, but it comes out squared. So we'll have a squared times the variance of x. And what about the b? Okay, for variance, it just disappears. Okay. And so we'll just have a squared times sigma squared. So again, that's just kind of our nice little review. Notice this isn't actually anything new. We're just reviewing here. Let's look at our next one though. For example, 143, let's say that x1 is normally distributed mu1 sigma squared 1, so that's our mean and variance. x2, same thing. And they're independent random variables. Okay, so what would be the expected value and variance if I add them together? So y equals x1 plus x2. So the expected value of y, well, that would just be the expected value of x1 plus x2. And if you're doing expected value, you can just take the expected value of each one individually and then add that together. So expected value for x1 was mu1, and for x2 it was mu2. So in other words, it's saying if you have two random variables and you add them together, you can just add the means. And variance is exactly the same thing. So variance of x1 plus x2 would just be the variance of x1 plus the variance of x2. Or in other words, sigma squared 1 plus sigma squared of 2. So add your means, add your variances. Those are nice simple rules. I always like those. They seem like they should fit. So now we have our official rules for linear combinations of normal random variables. So it tells us if x is normally distributed, a and b are constants, then if you have y, which is equal to ax plus b, it will be distributed normally with a mean of a mu plus b and a variance of a squared sigma squared. So that's just what we came up with up above. And if you're adding two random variables, then it will still be normally distributed. You add the averages, add the variances. And do you remember back in 2.6 we had one more formula for the average? So x bar is distributed normally with the mean mu and sigma squared over n. Now, all of that doesn't seem like we learned anything new. The new fact, the important fact, is that the new fact is that if you have ax plus b, or you multiply by a number, or you add a number, or you add two normal variables, or you take the average of normal variables, all of these were normal to start with, then any of these combinations are still normal random variables. That's very important. Adding numbers, adding normal random variables, they still end up being normal. Also, notice here when you take the average that your variance is now sigma squared over n on the average. Okay, and what that means, since our variance changes from our sigma squared to sigma squared over n, that means your variance is getting smaller. And what that means is that our average x bar tends to be closer to the actual mean value mu than individual random variables xi do. And we'll actually look at some things that kind of show us that later on. So how does this all come into play? Let's look at this one. The weight of salt packets are normally distributed with a mean of 0.2 and a standard deviation of 0.01. So number 1 says find the probability that a randomly selected salt packet weighs between 0.19 and 0.21 ounces. Now notice, this actually doesn't seem like anything new, and it's not. It just says one salt packet. So we're not doing anything special. We're just looking for the probability that x is between 0.19 and 0.21. And anytime you want to do this, you have to find your z-values. And so my first x value is 0.19 minus our mean of 0.2 divided by our standard deviation of 0.01 gives me -1. And our second z-value, we'll do the 0.21, gives me +1. Okay, so we found our z-values. So this is really the probability that z is between -1 and 1. So we're looking for the probability in between. To do that, you look up 1 on the table. When you look up 1 on the table, you get 0.8413, and look up -1 for 0.1587 and subtract. So you get 0.6826. So that's your probability that one salt packet is between 0.19 and 0.21 ounces. Now number 2 is where we get something new. Now find the probability that the mean or average, the average weight of 10 packets is between 0.19 and 0.21 ounces. So now we're looking for x bars. We're looking for an x bar, and we have 10. So the first thing you want to do is you'll want to say x is going to be distributed normally, and you want to know, okay, what is my mean going to be? How do I find the mean for x bar? Well, the mean for x bar is just always equal to your original mean. That's what my formula says right here. So for x bar, our mean is the same mu, but our variance we have to divide by n. So it's just equal to mu, which is 0.2 from up above. But then I did have a standard deviation of 0.01. Let's see, so my variance for x bar is supposed to be the old variance divided by n. Now my standard deviation was 0.01, so technically I'd square that and divide by n. Now n is how many packets you have. So in our case, 10 packets. So 0.01 squared over 10. And if you want to find the standard deviation, how do we do that? Just take the square root. So 0.00316. So before you do anything, you'll want to know, okay, x bar is still normal. You want to know what the mean is and what the variance and the standard deviation are. Mostly standard deviation. Once you've done this, though, it all ends up being exactly the same. So now we're looking for the probability that our average is between those numbers. So 0.19 is less than or equal to x bar less than or equal to 0.21. But now when I want to find my z-values, so I'm not starting with x's anymore, I'm starting with the average. So we'll do x bar minus the mean of x bar over the standard deviation of x bar. Since I'm dealing with an x bar, I want to make sure I use the means and standard deviation for x bar. So my first z-value, I have an x bar value 0.19 minus the mean of x bar is 0.2 and the standard deviation is 0.00316. So notice the biggest difference here is our standard deviation changed. So my first z-value is -3.16. And for z2, let's see, that x bar value is 0.21 minus 0.2 over 0.00316, which gives me 3.16. So coming back over here, this is now the probability that z is between negative 3.16 and negative and positive 3.16. And so anytime you want the probability for something in between two numbers, you look up each number on the table, find the two probabilities, and subtract them. Okay, or look up, do the CDF of 3.16 minus the CDF at negative 3.16, which is 0.9992 minus 0.0008, gives me 0.9984. So let's compare those two answers. The probability that one salt packet was between 0.19 and 0.21 is 68%. The probability that the average of 10 packets is between those same two numbers is 99%. So why is that? That's because we said up above we have less variance or less variability for averages, and so you're going to be closer to your mean. And so these two numbers, 0.19 and 0.21, those are close to the mean, and the average is going to be more likely to be close to the mean, so it should be even, it's more likely to be in between those two numbers, or closer to the mean of 0.2. So the biggest thing on these is making sure you find the mean and standard deviation right, and then it's all just kind of what we've been doing. So our next example, the mean pregnancy length of 266 days is about 0.73 years. The variance is 256 days. Let's assume that our lengths are normally distributed. What's the probability that a randomly selected woman who gives birth 4 times will spend more than 3 years of her life pregnant? And 3 years is 1,095 days. Okay, so there's a lot in there, but it's telling us that X is a pregnancy length. Okay. And X is normal. And the mean is 266. And the standard deviation is, oh, it didn't tell standard deviation, it told us the variance is 256. And that means then our standard deviation would be 16. So we have all of that. And it's saying, what's the probability that the total is more than 1,095 days? So let's say T is total of 4 pregnancies. And again, to do this, you have to do all of that work from just 2.6. So say, okay, how would I define T? Let's say T is the first pregnancy plus the second pregnancy plus the third plus the fourth. And if you know that, we also need to find our mean and variance. So the expected value for T would just be the expected value of x1 plus the expected value of x2 plus dot dot dot. Or the mean for T would be equal to, let's see, what's our mean for each one? The 266 plus 266 plus 266 plus 266 gives me 1,064. So that's kind of the average for 4 pregnancies put together. Now, if you want the variance for T, that should just be equal to, don't we just add up each of the variances? So we would do 256 plus 256 plus 256 plus 256 gives me 1,024. And I would also want to know what the standard deviation is for T. And to do that, you just take the square root of variance. So the square root of 1024 gives me 32. So after all of that work, I know that t is the total of 4 pregnancies. I picked t for total. And I found the new mean for the total, and I found the new standard deviation. And we know that if we add normal random variables, we'll still be at a normal random variable, so we can use the normal table. So now, coming back over here, we're looking for the probability that the total is more than 1,095 days. So what's the probability that our total is more than 1,095? And at this point, it's pretty easy, because you just do exactly what we did in all of 5.1. You say, okay, I need to standardize, so I'll take t, and I'll minus the mean of t, and I'll divide it by the standard deviation of t. And so we'll do 1,095 minus the mean of t, which is 1,064, divided by the standard deviation, which is 32. And once I did that, this t minus the mean of t over standard deviation of t changes to a z. So z is greater than 0.97. So here's my 0.97, and I want the area to the right. But if I look up 0.97 on my table, so that's the probability, so I'm looking for 0.97. Oh, no, that's not the probability, that's the z value. Z is 0.97. So here's my 0.97. Looks like the area to the left, or probability to the left, is 0.834. So this is 0.834. So here I'll do 1 minus 0.834, which gives me 0.166. So 1 minus 0.834 gives me 0.166. So there's about a 16% chance that she's going to spend more than 3 years of her life pregnant. With, again, the new part, or complicated part for this section being, you have to come up with the new means and the new standard deviations. Let's look at our next one. Let's suppose that the amount of soda pop in a 16-ounce bottle is normally distributed. So normal, with a mean of 16 and a standard deviation of 0.25. The amounts in the bottles are independent. Let's see, what's the probability that there will be less than 95 ounces in 6 bottles? So 6 bottles, that sounds like a total to me. So let's say this one is total is going to be like the first bottle plus the second bottle plus up to the 6th bottle, right? So now we need to find our new mean. And how do you find the new mean? You just add up all of the averages for each one. So we'd have 16 plus 16 plus 16 plus 16 plus 16 plus 16, or 96. And our variance, to do the variance, because we're just adding random variables, we would just add each of the variances. Now it doesn't actually tell us what the variance is. It told us standard deviation. Let's find variance instead. So variance would be 0.25 squared, which is 0.0625. So remember when we did chapter 2.6 or section 2.6, and I was telling you that it's always, all of these rules are always for the variance. So even though they give standard deviation and we want to get back to standard deviation in the end, we have to use variance for our rules. So we'll have 0.0625 plus 0.0625 plus dot dot dot, and we'll add them all up until we get to 0.375. And then so to find your standard deviation, you take the square root of that. So the square root of 0.375 gives me 0.6124. Let's see, so now they asked us to find the probability that there's less than 95 ounces in those 6 bottles. So we're looking for the probability that T is less than 95. So first step is always standardized. Now if this is a T, you'll want to minus the mean of T and divide by the standard deviation of T. So it'll be 95 minus the mean, which we said is 96, over the standard deviation of 0.6124. So once you standardize, that's a Z now. Z is less than negative 1.63. So negative 1.63. You want the area to the left. That means all you have to do is just look it up. So we'll just look up on our table our negative 1.63. And it gives me 0.0516. So only a 5% chance that they get less than 95 ounces. So let's look now at number 2. Number 2, instead of finding a probability, it just says what would be the mean and the standard deviation of the average amount in 6 bottles. So before we did the total amount in 6 bottles, let's now find the average. So for the average of 6 bottles, that means N is going to be 6. The mean for X bar, you can just use your formula. It's just equal to your normal mean, and our normal mean is 16. And then we had a formula that the variance for X bar is equal to your old variance over N. So our old variance is 0.0625, and we'll just divide it by 6, which gives me 0.0104. And to find the standard deviation for X bar, you'll do the square root of that. Which is 0.1021. Okay, so we found the mean and standard deviation for the average. And then if you wanted, you could go ahead and find probabilities just based on what we're doing. Instead of T's, you would just have X bars and everything would go on and be exactly the same. So one more practicing of, now let's see what would happen. What's the mean and standard deviation of the amount of soda if we measure it in liters? Notice this one doesn't actually say for 6 bottles or averages or anything. So this is just one bottle still. So it's just one bottle, but change to liters. So let's say Y, just because I'm picking a random letter, let's say Y is 1 bottle in liters. So how do you get Y? It says a liter is an ounce divided by 33.8, so that means that Y would be equal to our old X divided by 33.8. Or, if you prefer, it's 1 over 33.8 times X. So now to find the mean and standard deviation, what's the mean for Y? If you're looking at means or expected values, what happens to that number? It just comes right out, right? So it's going to be 1 over 33.8 times the mean for X, or 1 over 33.8 times the old mean, which was, what's the old mean? 16. Or 0.00185. So that's what the mean or the average would be in liters. How about 0.473 liters? That sounds more accurate, right? So we found our mean. We also need to know our variance. So we want our variance. What happens to a number, though, when you're multiplying for variance? What happens? It comes out, but it comes out squared. So we're going to do 1 over 33.8 squared times the old variance. So 1 over 33.8 times our old variance, which it was 0.0625, gives me, oh, I didn't square that when I wrote it down again. So this one is pretty small, 0.00055 is my variance. And I definitely ran out of room there. But the standard deviation would be the square root of that, 0.00055, which gives me 0.0074. So we found the mean and standard deviation. And with that, then you can find probabilities. It would just be whatever your value is that you're interested in minus this mean that we found divided by this standard deviation. And one more example that was on the video you should have watched.